Okay, welcome back. This video is going to be how we can use factor and remainder theorem to factorize complex polynomials instead of just complex quadratics. So we need to do more than just factorize complex numbers in the form of a quadratic. We also need to be able to factorize complex numbers in the form of a cubic, for example. So the word polynomial, it's a little bit of a weird term. It just refers to some kind of algebraic expression. Normally in the past, we've looked at this with x's, so something like, for example, something like, x cubed plus 2x squared minus x plus 3 might be a polynomial we've looked at in the past, or a cubic we've looked at in the past. In this case, we're essentially looking at expressions like this and trying to factorize expressions like this, except instead of my x's, I'm going to replace those letters with the complex number z, just like so. So just like how with normal algebraic, with real numbers, I can factorize quadratics, I can factorize cubics, I need to be able to do the same thing with my complex numbers. Factorize quadratics, factorize cubics. Now the process for factorizing a complex number, that's the form of like a cubic, for example, is very similar to factorizing a normal real number, something with x's in it, in the form of a cubic. The way we do both real or complex numbers is by using our factor and remainder theorem. Now, the slight wrinkle or the difference to what we've done kind of earlier in high school versus now is instead of just knowing how to use our factor and remainder theorem, we're going to look at how we can actually prove our factor and remainder theorem, and we need to know how to replicate this in exam situations. Now, in order to understand how to prove our factor and remainder theorem, it can be easier to ground this in more familiar concepts, such as looking at a standard real number quadratic. So before we get into the algebraic proof, let's just quickly highlight the idea or the theory behind why this works. If I take a quadratic, let's say something that I can easily find the roots of, something like x squared, let's just do plus 5x, let's do minus 6, make it a little bit fun. Wait, does this work? Yeah, that'll work. Okay, so let's say I have a quadratic like this here on the screen. Well, some of you might be able to factorize this immediately, but let's do this via division to show how I can factorize by using division to factorize any kind of polynomial. In this case, I'm going to use a quadratic. A quadratic does technically come under the umbrella of polynomials. Okay, so if I divide my quadratic by something that is not a factor, so I'm going to actually pick numbers that I know for a fact isn't actually going to be a factor of this quadratic. Let's divide by something like, let's do x plus 4. Okay, let's divide this quadratic by x plus 4. That's not a square root symbol, that is a division symbol. It's going to be x squared plus 5x minus 6. I'm just going to quickly recap long division, but this should be a skill we have some memory of, so hopefully this will just be a nice little quick refresher on a more simplified question. So in order to do my polynomial long division, I take the first term and I divide that by my first term over here. X squared divided by x is simply just going to give x. I'm now going to multiply that back in. X times x is going to give x squared. X times 4 is going to give plus 4x. I'm now going to subtract these two lines. X squared minus x is going to give 0. And then if I have 5x minus 4x, that's just going to give positive x. If I now divide these two terms again, now it's going to be that x divided by this little x down here. X divided by x is simply just going to give positive 1. Substitute that back in. 1 times x is going to give x, and 1 times 4 is going to give plus 4. Again, I'm going to subtract. And just to refresh our brains, every time I do this process, I should find when I do my subtraction, I always wind up with a 0 term here, and I'm going to get a 0 term here as well. So I'm happy. Now I'm going to do negative 6. Or if I like, I kind of bring my minus 6 down here. I could just travel this down here. Negative 6 minus 4 is going to give negative 10. So I can say for this particular quadratic, I have a remainder of negative 10. So let's just write that at the top. My remainder is going to be negative 10. Okay, if I come down here, I can write my polynomial as being x squared plus 5x minus 6 is equal to x plus 4, x plus 1, let me fix that 4, minus 10, because my remainder here is negative 10. Now, I can test this. If I expand everything out, I actually will get back to my original. So these two expressions are equal to each other. X squared plus 5x minus 6 is equal to x plus 4, brackets, x plus 1, all in brackets, minus 10. Okay, now the reason I've chosen to write it like this is I want to assign some algebraic terms to this process I've done here in order to get some kind of proof which I can represent algebraically that can apply to any type of polynomial. So, like I said, I want to assign some terms here. Well, this here is my divisor, so I'm going to call that d of x, where x here is my unknown variable. Well, this part here under my square root, this is actually going to be my polynomial. We'll call that p of x. And my solution at the top here, well, this is going to be what we call our quotient, or, the solution when I do my division. Now, this negative 10 part, I'm going to write this bit in purple. This, of course, is my remainder. Now, because there's no, x variable as a part of this, I'm just going to leave it as simply just being called r, because it's just a whole number term. And when I'm doing this for the most part, at least for this theory or for this proof, I'm always going to be getting some kind of whole number remainder. So let's rewrite all this new terminology as a line very similar to the expression I've got below. This means I have p of x is equal to d of x multiplied by q of x. And in this case, it's going to be plus r. If r is negative 10, it's going to become minus 10 like above. So this is kind of an algebraic way to express the solution of any polynomial. So any polynomial is going to be equal to whatever I divide by, multiplied by whatever the solution from that division, plus my remainder. And again, we can kind of prove it with real numbers above here, because you can see if I expand that, these two sides do balance. Left-hand side equals right-hand side. So it is going to be true for any polynomial. Now, if we have a little look at my divisor is x plus 4. Well, for my factor and remainder theorem, this only really works when I have a binomial divisor, which means I have two terms in my divisor. So instead of writing my divisor as just simply being d of x, I could write this as being x minus a. Okay, where I always have x, some x term, minus some kind of whole number. Now, in this case, if it's x plus 4, then that simply means that a is equal to negative 4, and I wind up with that double negative situation to create my positive solution. Now, there's a really important reason why this has to be negative, and we'll kind of show it in our proof. And it's based around the proof, it's x minus a. So if I substitute this x minus a part in place of my divisor d of x, then I get this expression here. My polynomial with respect to x is equal to x minus a, all in brackets, q of x plus r. If this here is true, let's scroll down just a little bit here. Let's just scroll down to here. Now, if this here is true, what happens if I substitute in my letter a for my polynomial? In other words, if I take p of a instead of p of x, let's just explore what happens. If I do p of a, that's going to be equal to all my x's times a's, that's going to be a minus a, multiplied by q of a plus r. So if I have p of a is equal to a minus a times q of a plus r, well, all of this part here is simply just going to equal 0, because 0 times any number gives 0. So what I'm left with is my polynomial, if I substitute in a instead of z or instead of x, is going to be equal to my remainder. This is my remainder theorem. Now I'm going to test that with the polynomial above. You can see I have x squared plus 5x minus 6, and my remainder in this case was negative 10. What I divided by was x plus 4. If I substitute negative 4 into my polynomial, because remember, it's kind of opposite day because I have a negative sign here, so I'm going to swap my signs. If I substitute negative 4 into my polynomial, I should get the answer of negative 10. If I test that, that's going to be negative 4 all squared plus 5 multiplied by negative 4 minus 6. And if I crunch my numbers, negative 4 squared is 16. So I have 16 minus 20 minus 6. Well, 16 minus 20 is negative 4. Negative 4 minus 6 is negative 10. I've now proven that if I substitute in my a value, where a is kind of the whole number I'm using in my division, but I'm going to swap my signs, I will get my remainder for any polynomial. Quadratic, cubic, quartic, you name it. This is going to work for any polynomial as long as my divisor is going to be a binomial term. So an x minus a type of term, this will work. This is the remainder theorem. And why this is so important is I can use this to identify factors of any polynomial in order to simplify my factorization process. For example, take the number 25, for example. If I have the number 25, if I divide 25 by 5, I get 5 remain to 0. Whenever I have a 0 remainder, it's because my divisor is a factor of that number. So for example, with 25, 5 is a factor of 25 because 5 multiplied by 5 gives 25. So if I get a remainder of 0, I have now identified a factor of my polynomial. So I can use this theory, this remainder theory, to identify factors, that's the factor part of the factor and remainder theorem, of any kind of complex polynomial. Once I've identified those factors, I can now use polynomial long division to fully factorize any type of polynomial with complex numbers, specifically cubics.